workshop, I'm going to be presenting something of the last couple years, actually, very recent research that we've been doing along with some of our industry partners on electric energy storage systems, which is on batteries, and how to increase lifetime of batteries, charging algorithms for fast charging of EVs, so on and so forth, and some of the new work which are data driven based battery management systems for e-mobility. So first and foremost, I'd like to present work that was done by Dr. Lalit Patnaik, Dr. Vinicius Marcis, and Dr. Praneeth Jayasai as a team to develop a new charging algorithm, which is a new constant temperature, constant voltage charging algorithm, where we take into consideration the health of the battery while fast charging, right? So that it is temperature dependent, and how we start looking at temperature as a important parameter that defines health of the battery. So of course, DC fast charging systems are anywhere above 50 kilowatts and above. So as you may know already, the standards are set in SAE J1772 standards, level 1, 2, and 3 DC fast charging. It starts from 36 kilowatts onwards all the way up to 250 kilowatts. So currently in the market, you can even get 350, 400, or 500 kilowatt fast chargers. We ourselves have one which is rated at 350 kilowatt, as you can see here. We work closely with a company called eCamion, and we have some funding from the government of Ontario to do this work. So, as you will see in set here, this is of course a high demand because they can fast chargers now is in high demand in terms of infrastructure in electrification, and so as to charge vehicles within 5 to 10 minutes of charging time to recuperate up to 50% to 60% of the state of charge. So having said that, the idea here is to charge um, in a constant current mode, ideally for lithium ion phosphate like LFP, popularly used batteries, or NMC type of battery, which is nickel, manganese, cobalt chemistry of lithium. They usually use CCCV, and so constant current, constant voltage. Now, how it works is very simple. Obviously, constant current, constant voltage, in the best analogy I can give you, is uh, in terms of a rubber ball, right? I mean, if you tie a stone rather at the end of a rubber band, and if you just jerk it, you will see that the stone starts to bounce around, right? That jerk that you gave was a constant current. That is analogous to a constant current, but the bouncing of the stone, the reaction, is the voltage. That voltage actually has takes time to settle. Okay, that is my best analogy I can give you in terms of constant current, constant voltage. So now, when the constant voltage is reached, that means it has tapered off and you have finished charging. So then you can reduce the force of the current in that case. So when you see this plot, if you follow my pointer, if you can see on the screen, constant current is applied while the voltage is in transient state, like it has not reached constant voltage. However, with that rubber ball or stone analogy that I gave you, it will remain constant. Your current will come down. So many of you who probably are in this area know this quite well. Um, and this curve actually gives us a lot of information, such as the charging current rate, which is 1C, 2C, 3C, whatever it may be. C rate means 1C rate means, for example, if you have 100 amp hour capacity pack, let's say you are passing the rated current, which is 100 amps, so that you can charge the battery in 1 hour, basically. So the C rate is 1C. 1C is the rated current. However, batteries or lithium batteries seldom work at this, very rarely rather work in this area of operation at 1C, because 1C is considered fast charging. Zero point 0.5, zero point 0.4, 40 to 50% of rated current is the rated value at which it is usually operated, so that you cannot so that you don't destroy the battery in terms of the temperature and capacity fade. So as you can see here, the blue curve, this, sorry, the dotted curve, it will show you the charge capacity rate, for example, constant voltage area, which is the red area, with the capacity relationship, charger float voltage, it will show you in this region, yellow region. So the charging current, as I said, is this blue curve, starts with constant current and then tapers off. So these are all very informative parameters which we use in order to gauge or design battery management systems. Now, fast charging or ultra fast charging now started having um, more impact in the market, where they're saying, well, how about 2 times rated current or 3 times, 4 times rated current? So that 100 amp hour battery now would be up to 300, 400 amps in order to charge in 1 hour. Or if you have to charge in half an hour, you go even double of that. So it's going to be very challenging to design BMS and to design the cell balancing units where we have the power electronics managing the cell distribution, current distribution among the cells in the pack. Like there are about 8,000 to 10,000 cells in a Tesla Model S, for example. You will find that each cell needs to be monitored, each cell needs to be balanced with the other cells so that the voltages are constant of each cell so that there is no circulating current. And that's a challenge, right? So power electronics challenge. So those are some up and coming research areas for us to focus on in terms of the BMS, quote unquote. So yeah, so again, why this C rate is so important? Because you will see this plot here from some experimental data from our lab. We can see the capacity on the x-axis of a battery cell, one cell, right? And the voltage of the cell here. So typically the voltage starts at around 4.2 to 3.8, anything like between this range for the LFP cell, lithium ion phosphate cell. You can find this as open circuit voltage. It starts from there. So 0.2 C, as you can see, charging gives you an interesting number of capacity, which is 2 amp hour, which is the rated capacity. However, when you start to go to 2C, so 0.5, 1 and 2C, we did some tests to see that the green plot actually starts to tend to reduce the capacity over time. So as you can see, the capacity starts to fade. Even the voltage is quite low starting from 2C. So it's a challenge to bring this curve up to this point and still make sure that the battery is healthy. So that's the challenge. I thought that this plot gives you a lot of information. This chart actually gives you a lot of information and sets up the rest of the talk and the work that has been done by Lalit, Vinicius, and Praneeth, and the impact of that work for our industry partner. So charging rates, we started to see fast charging, right? Fast charging algorithm. So the CCCV was the first one, which I already talked about. It is well documented. As you can see, several authors have actually referenced. There are several references for this work in the 2000s, then late 2000s, early 2000s, and into the uh, 2000s till 2008. Multi-stage constant current came about in so as to give fast charging in discrete time steps. Again, several um, authors have worked on that, and it is a very popular algorithm in the industry as well for all those fast chargers we have been talking about. 4C, 1C, pulse current. Again, another very popular algorithm is the pulse current. As you can see here, it has a ripple frequency of about 1 kilohertz, and it continues until it is charged. So you can have this upper limit to like 3, 4, so on and so forth. So here I'm just showing you an example of a 2C rate peak of this pulse fast charging. Again, there is a company that we are working with here in Canada and Ottawa who use pulse charging for their battery packs. They are a company that makes BMS and algorithms, fast charging algorithms. So we connected with them and we have a funded project. They are working on this pulse charging, but um, we've also proposed to them, instead of going square wave, why don't you go sinusoidal? You have more control over that. Yeah, it could be done trapezoidal, whichever. I mean, you can try these yourselves. when you are working in your research, if this is your area, you can have shapes and see the impacts of the pulses on the temperature, on the charging rate, etc. So several fast charging algorithms exist. However, there was a new algorithm development need in the industry where it takes into account health. So there is no charging profile that does not hamper health, fast charging. And this is, I will be very blunt about it. This is the main motivation for developing a new algorithm because of the shortcomings. So they don't adjust all those charging algorithms that you saw. They do not adjust for the aging or temperature of the cells, and they tend to be very conservative, right? The main idea here is that there is a lot of cell degradation due to uncontrolled heating. So we have to ask the question to ourselves, well, so then, well, which charging profile can we devise or design so as to ensure the fastest charging time without hampering the cell life or health? Now it starts from cell level. Obviously, we have gone to modules now. We are looking at 16, 8 by 2. So 8 series, 2 parallel. For example, we go 4 by 4 as well. So 16 cells modules also we have graduated to from this work, but this work is more mature. So that's why I'm presenting this one. The 16 cell is under development, and you'll see it in a recent publication upcoming. So once it's published, I can share the information. But yeah, so I mean, but anyway, the crux of it starts from the cell itself. So it's important to have the cell model, etc. So yeah, so this is important for us to know this profile, fast charging profile, so that the health is maintained. So we started to compare our thought process of charging profile with the constant current, constant voltage, which is the popular one. I mean, it's the most popular, no doubt about it. Fast charging companies who are building fast chargers embed the charging algorithm, CCCV, uh, which is the popular one as a fast charging algorithm. So now let's take a look, and it's very interesting. CC means 1C. Okay, so at 1C rate, they start charging. The open circuit voltage is reached. They reduce the current. We see the temperature profile from experience. We started to log a lot of data, and we started to look at the temperature rise. So temperature of the cell on the surface of the cell, we started to measure with sensors, obviously. So the measurement of the cell temperature looks kind of like this, like a bell curve. Okay. Obviously, it has a much more latent time because it is temperature versus current. So the current, as you can see, is constant, but the temperature takes time to reach its steady state. Or steady state, or I should say not steady state, but maximum temperature. There is no such thing as steady state temperature. Um, so maximum temperature, depending on the non-linearities of the cell, etc. And then obviously, as you reduce the current, that thermal temperature rather will go down, right? Will lower. Now we saw an opportunity here in that there is a temperature rise that is stipulated by the manufacturer of the battery. They are saying, well, delta T should be between 5 to 8 degrees Celsius. Okay, so that's fine according to the sheet, manufacturer's data sheet. We say, okay, we will maintain that, but why not utilize this shaded portion and come to the maximum quicker? It's okay if we can come quicker, charge it even faster, but maintain the temperature at the constant temperature rate. So there is a constant temperature here. Instead of looking at constant voltage in the sorry, constant current, constant, we can go for a constant temperature so that the current can be adjusted. Okay, so current profile can be adjusted such that constant temperature is reached. So what we did, this red curve is the proposed temperature. You see it is going up. It ideally would be a square, but yeah, it will take some time. So obviously reaching that constant temperature, so all this shaded portion is utilized in the start. And what that means is the current, you see, from 1C rate we can go to 2 or 3 or 4 or whatever it may be, uh, in this way, such that it comes up to the CCCV when the temperature has reached constant and we have reached this CCCV point. Once the CCCV point is reached, then it is the CV algorithm takes over. The current comes down, just like we did in the CCCV mode. So what we have achieved by this is ultra fast charging, which is obvious from the plot. Same temperature rise, same temperature rise as the CCCV mode. Now you have flexibility of adjusting the current profile for each cell, and this profile takes into account aging of the cell. Like if the cell has aged, let's say in a year or 2 or 3, you can still do fast charging on that cell, making sure that based on that cell's thermal capacity, you are keeping the temperature constant within the stipulated limits. This is very, very important. In fact, this work was published in a transaction paper. You can refer to the note footnote over here, and you can see Lalit was the first author. I don't know if several of you may know Lalit or may or not. He was from IIC. Of course, he worked with Dr. Umanand long, long back. Geez, what is it? 17, 16, 17? So, yeah, 15, 16, 17, 18, in that range, 2018. So he joined our lab and as a postdoc, and worked quite well building our lab in these areas of thrust. Um, so yeah, commendable work by Lalit. So this is the block diagram, very simply put. In the interest of time, I'm going to go a little bit quickly. Yeah, very simple PID controller, because obviously you're taking the feedback of temperature from this lithium ion cell, putting it in the comparator. The PID controller is enough because of temperature being a large thermal time constant, as I told, in minutes typically for one cell. So, and of course, as you go larger modules, packs, and more homogeneity comes into being, then the temperature constant even becomes higher, like minutes and hours put together. So for a cell in minutes, so we really don't need a very fast control loop. So a slow control loop is permissible. And then of course that current command is added to the feed forward command, which is our algorithm. Basically the curve that you see here, right? The proposed charging algorithm, which goes to the charger, which is basically a power supply in the lab. And then basically that is charging the lithium ion cell. So if you look at the simulation results, we've taken a simple cell model, second order cell model, electrical model, as well as a thermal model. So the ECM, which is the electrochemical cell model, and the thermal model, which is the ETM, electrothermal model, are both second order models. And you can, if you have worked on batteries, you would appreciate these two models, which are very popular and standard in literature. So the results show in terms of simulation, of course, I won't go the details of the control parameters and the internal resistance, etc., etc. But you can see very simply, of course, we've done approximation for the charging current, which serves as the feed forward term in that block diagram here, right? So the red one is the charging algorithm. For different internal resistances, we take the internal DC component and the AC components of the model as one internal resistance, and that internal resistance we have varied between 0.08, 0.06, and zero point 0.1 ohms, right? Just to see the effect of the charging current. Blue one is the voltage, open circuit voltage, and finally the temperature. So the black one, as you can see, is a constant temperature, right? What we have tried to achieve in our work. So that so the simulations are holding true. Then we go to the experimental test bench, as we typically would, and then start working on. So this was a Samsung 18650 cell, just so you know. Um, we have the temperature sensors, the power supply, as I told you, for the power source as a charger, and the PID controller sitting in the middle of it. Of course, we use the hardware in loop. Here you can see the experimental setup in real time on the desk. So yeah, Samsung cell, which is an NCA cell, nickel cobalt aluminum oxide chemistry, 3.6 volts open circuit voltage, 2.3 amp power capacity. So we did a discharge tests first. We have a reactor, Turnigi. Reactor Turnigi is the company that has this reactor balancer charger discharger. So we can plug the cell in it, and we can go up to 20 amps of discharge current with an appreciable ripple. So this is just to test the discharge capacity in order to compare all the charging techniques that will follow. So we did the charging at 2C rate. So 2.3 was the, as you saw, was the 1C rate, 2.3 amp hour. So we went to 4.6 amps, right, in order to charge within 1 hour. So we went to 4.6, and you can see here the voltage matches the open circuit. The blue one is the CCCV, red one is our proposed CTCV, constant temperature, constant voltage. Yeah, so the temperature on this plot, as you can see, the blue one is the CCCV, as I had told you. As we expected, this is the rise, the pattern of the temperature rise. And finally, you can see the red one, which is our constant temperature, constant voltage algorithm. So yeah, it's clearly you can see the delta T we have maintained, the maximum delta T or temperature rise within limits, which is between 5 to 8 degrees Celsius at about 7.5 degrees Celsius, right? Which basically means because of doing these faster charging, we have reduced the charging time from 0 to 100% SOC, reaching in 20% reduced time. You can see that even here, right? Yeah, between the difference between the blue curve, which is the CCCV, and the CTCV. So just proof of concept from the experimental standpoint that the algorithm works for a stipulated temperature rise, keeping temperature under limits. We can still work with the fast charging algorithm, which was for the first time proven practically. Like, I mean, in literature, it was not available. This type of stuff was not available till a couple years back when we published all our work here. So this is just the data from that. I'm going to skip some numbers. We don't really, it's just the same stuff that I just told you in words. 20% faster charging rate. And this is all the data that we have taken, the time for CCCV, time for CTCV, percentage reduction in charge time, etc. Right? And the SOC percentage. Well, an interesting test also on the flip side of the coin, we said, well, today's day and age, fast chargers are using CCCV. So that means they are increasing, the charger companies are increasing the current rate, the C rate, but still keeping the algorithm CCCV. So what is happening? If we increase 25%, let's say, for instance, we said, okay, let's do a test just to see 25% increase in C rate. So 1.25 C. So we kept it at constant at 1.25 C, and the original algorithm of ours at 2 C. So yeah, I mean, you can see charging rate matched, right? You can charge the same cell in the same time, like 70 minutes over here. I think it is, yeah, right, between 60 and 80 minutes, 70 minutes. You can charge it. Very great, good. However, yeah, this also proves this plot is actually the state of charge versus time. So you can see they are matching at 100%. But now, and of course, voltages are matching. Is the temperature, right? The key thing here is the temperature. So you can see clearly the blue one, which we increased 25%, the temperature has gone above the stipulated 8-degree mark, which is 9.5, 7.5, 9. Approximately 2 degrees Celsius change between the surface temperature of the CCCV algorithm while running in CCCV 1.25C and our algorithm, which is running at 2C. So it's incredible, right? To see that this temperature rise, that's only with a 25% increase. Now you're talking 200, 300% increase, 400% increase. This temperature is ballooning inside the cell and eventually in the modules and eventually in the pack. At cell level, it is scary enough. So I can't even imagine. So when that happens, capacity or amp hour capacity to hold charge reduces the cell, which is, I think, important to note. And that's why this work becomes even more impactful. And so designing based on this data, we are now working on designing some active materials for thermal management, BTMS, battery thermal management systems, dynamically changing of course, that's some mechanical engineering work with some of our colleagues in mechanical engineering. We're also devising cell balancing techniques so that the currents are kept within limits and so on and so forth. So, but this data becomes very important. Yeah, cooling also is very important. How you cool the cells. So I mean, you look at this different cooling. If you cool it well, you can even reduce the charging time further. So the blue one is with good cooling, like forced air cooling. We introduced a fan in the experimental setup and saw the cooling effect that it's gone down to 1 hour. From 70 minutes, we are gone down to 1 hour. Bad cooling or thermally insulated cells will obviously give you longer time, right? Because the temperature is that much higher. So yeah, those things also affect quite a bit. We started to move towards also estimation of temperature based on current profiles, voltage and current profiles with advanced modeling of cells, thermal models, high order thermal models, etc. So here you can clearly see one of the estimated in blue, red is the measured actual temperature. So you can see our work, which is now progressing in terms of sensorless implementation, so that we don't use sensors on the surface of the cell. Like I said, in a Tesla, you have anywhere between 8,000 to 10,000 cells. Um, Imagine the harnesses, right? I mean, if you are putting sensors on on each cell, I mean, the theory works, no doubt. We saw that it's easy. It's like a project, simple thing that we can all implement. Nothing too complicated about it. But the complications arise when they say, well, when I went and presented this at a non-IEEE conference, which is funny. I go to a couple of these every year, and I take a battering from industry. The industry says, hey, great theory and all that. It's great for academics and publishing. What is the practicality, right? So the sensors really need to go. They said, forget about it. We are not putting sensors on 8,000 cells. Uh, and unfortunately, this is the downside of this work. But so now we've started to um, focus on our sensorless techniques, which is core temperature estimation in the second half of this lecture. In the next 20 minutes, I'll talk about that. Some wireless BMS so that we reduce all the wires, sensors, voltage sensing, current sensing, all this stuff, take it to the cloud, right? And that's why I talked about data centric BMS as the second half of this lecture. But it stems from this work, right? So, sorry, excuse me. So, this is why this work becomes important. So, sensorless work we started removing the sensor from the thing, estimating the temperature, the blue curve, but still there is an error. In the first cut of our work, we saw 1.4 degrees Celsius error, which is a lot. I mean, considering 8 degrees is the temperature rise, 1.4 is a big percentage. So more accurate temperature estimator is required, which means we have to move away from the second order thermal model, electrothermal model, right? You are also, another thing is that internal resistance we are considering constant. So we have to move away from that also, because with time and aging, that's going to change. So you need a more accurate estimate. Anyway, this is some of the performance comparisons with some of the previously proposed fast charging algorithms. So as you can say, you see, you can adjust to the thermal environment quite simply with and accurately with our proposed algorithm. This is just going through some slides with the experimental setup, data acquisition, the MATLAB scripts, the MATLAB SCPI, where you have the control, the automation, reliability studies, etc. You can see here we have a thermal chamber in the middle of it where the battery under test goes. This is our automated test system, which we are making a niche. There is no such system out there in terms of testing batteries, and with health considerations and temperature, there's no work out there from companies like NH Research or Amitech, or even for that matter, uh, uh, um, what is that other company which makes yeah. So anyway, there is a plethora of companies out there now into battery testing, but getting to this is a niche, right? So we're working with another company here in Toronto, but it's a global company. So building a automated test system. So it's a work in progress as well. Yeah. Yes, charger, the power supply, the load, very simple lab setup, just showing you some components here. Analog measurements from the Chroma 66204, which you probably have in the lab as well, some of you. Temperature sensor LM335 from TI. So Vinicius built this setup. As you can see, the temperature chamber. Temperature chamber goes from anywhere from -40 to plus 125 degrees Celsius. It does have capability of Modbus communication port. Um, During COVID times, in fact, we used to run the experiments from home and collect the data on our laptops at home, which is incredible because we couldn't stop our work, and it was difficult to get into the lab during these last 2 3 years. COVID time was horrific, unfortunately for all of us, especially with the experimental results, right? Experimental work. So anyway, this is something, and this is a imaging camera placed inside the chamber while the test is running, so you can see the behavior of the cell, or if any failure occurs, we can monitor that. Yeah, thermistor assembly for the sensor. So here is an interesting thing, right? So somebody said, okay, again, one of these conferences where they say, industry participates heavily. They said, hey, you are putting the sensor here. Okay, great. Now, okay, if I flip this cell, turn it around and put this sensor on the other side, here, what will be the difference? So I said, yeah, we have noted huge temperature differential, like between two, no two spots on the circular surface, say, of the cell is the same, which is another issue. It's not homogeneous, the surface. So, so we started to do some work on core temperature estimation now, right? Core temperature is in the middle of the cell where the material is homogeneous enough, so we know the temperature is accurate at any two spots anywhere in the core of the cell. So it's really a lot of material science, started to read some electrochemistry journal papers and stuff like that. We've started to have such a lot of how you say cross-disciplinary work that we started to appreciate. So in summary of that, basically, I already talked about all this: smart charging scheme, adjusting for the aging thermal environment, adjust the charging current in response to the condition of the battery, actual health of the battery, faster charging for a given amount of degradation, lower temperature rise for the given charge time. We proved that as well. It enables a controlled aging and degradation. So now by varying the battery temperature, you can, by based on the value of the set battery temperature, you can enable this aging and degradation controlled in a controlled fashion. And the best part about it is very low cost, low bandwidth PID control with a feed forward aid was used. In terms of the data-driven techniques for the next 15 minutes or so, 20 minutes, I know we started little late, so maybe 15 to 20 minutes, I want to talk about some of these data-driven BMS. And that's, of course, work also by the group, Akash Samanta, Lata Nikal, Alvin Hyun, Chandan Chetri, and Dominic Karnem have started work in the last couple years on this effort, right? So some data-driven techniques. So BMS in general, right? Battery management system looks like this. Like this is the whole architecture, including powertrain control, DC-DC converter going to the 12-volt rail, the drives part, etc., etc. But the battery management system sits in the center of it. And of course, if you have been following much of the work by TI or Analog Instruments, a lot of them have BMS chips, which actually right now do the job, right? So in that is the battery monitoring unit, which is a very, very critical part, which is the battery SoC model sitting in the middle of it, basically talking to a CAN bus, right? And through the communications, giving commands to the energy demand unit. There's also the battery control unit, so that you can have charging and equalization commands that are given back and forth between the battery and the control unit. So here you can see all the functionalities of the BMS. I don't need to go into details much here. It's control, parameter estimation, diagnostics, and data storage. Some of the key functions of BMS, right? But more recently, we've seen we need state estimation to be very, very accurate. One of the key functions is state estimation. As you can see, parameter estimation. We started to zero in on that a little bit so that you can appreciate why accurate SoC estimation is very important. State of health or state of power or state of available power, remaining useful life prediction, so on and so forth, because of safety issues that we have seen recently. Also, range anxiety. Now, battery state of health is very, very important. This animation on the left hand side shows you the available capacity and how, as the available capacity dwindles and aging happens, the state of health goes from 100% to zero, right? So, it is the capability of the battery basically to hold the or retain the charge compared to its rated capacity, which is on the left hand side, the total rated capacity, as I showed you. So it needs to, your model that you develop needs to consider this aging, which is not an easy task by any stretch of imagination, because there are certain factors, so many factors that go into aging. And that chart is shown over here. The causes, the degradation mechanisms, the degradation modes, and the effects, right? So capacity fade and power fade are two of the main effects, eventual effects of aging. So I will leave it at that. I don't want to go through each and every, because each and every cause is interrelated with the degradation mechanism, which is further interrelated to the degradation mode, which are three primary modes, and finally the effect. So I'm not going to go into details of this. Um, but you can find these in several publications. So traditional BMS versus wireless BMS. So we started to think ourselves, let's start to look at cost-effective um, battery management systems. So this is a Tesla Model S on the left-hand side with traditional BMS, right? So you can see 85 kilowatt hour pack in the Model S version 1.0, 16 by 432, so 7,000 cells nearly, 18650 NCA cells. 18650 basically means 18 by 65 Nothing fancy about it. 18 width and 65 height, right? So 18650 NCA. This is the traditional BMS. So you can see it's a jumbled up wires all over the place, right? So all wires and harnesses and sensors and of all types. We are proposing something which is a novel concept of wireless BMS, which is of course catching on. It's not as novel now. In the last 5 to 6 years, this has been catching on big time. You even have products today from TI and Analog Instruments on wireless BMS. So basically, moving from the wired architecture that I showed you, which is really jumbled up, to something which is neat and clean and has no wires and sensors which are unnecessary. You can build models, put them in the cloud that can actually run from a server somewhere, and you can have transmitters and receivers, wireless transmitters and receivers that actually give the control signals to the batteries to behave the way that you want. So why do you need all the wires on board? So getting rid of these wires, in fact, saves you about quite a bit of tonnage in the weight, right? So kilograms and hundreds of kilograms of weight that you can save from all this wiring and harnesses on board, which basically means you can improve the range of the EV itself. Okay. Wireless by BMS architecture, just the functionality wise is all the same. I'm not going to repeat and beat our head on this. We don't need to do that. But the key part takeaway here is that all the functionalities, even though they are common between the WBMS and the wired BMS, the information exchange is among each of the sensor nodes and the master controller unit, right? So as you can see, the BMS, the green portion here, has the master controller embedded in it. All the dotted lines are all wireless communication lines. So voltage, current, cell voltage, temperature, etc., etc. They are basically sent from wireless modules and received by the by a model of the battery, which is the state estimator. Okay, at the end, and then of course the state estimator gives you, the master controller, all the information it needs in order to take decisions of thermal management and electrical energy management. That is the top one, thermal management, and the bottom one, which is the charging and discharging of the cell equalizer. So very quickly, very simple: state of charge, state of power, state of health, remaining useful life. These are examples of what the state estimator will tell the master controller. So these are some of the objectives of developing the WBMS. Again, like I said, it can go up to 200 pounds per vehicle. You can save a lot of wiring harnesses, and all this I already talked about. You can, reduce fault diagnosis, reparation time, reduce the complexity of the design, very simple, clean design, modular design, where you can add master controller or master slave architecture, where you can have a master node and you can add more batteries or cells if you wish. or delete for that matter. So here you can see, right, battery monitoring interactions within a CAN bus system, and battery monitoring and additional sensor interconnections with a smart mesh WSN. So here you can see you have one of the master nodes which is communicating with all the sub nodes. You can add battery cells and delete as you wish from this master one node itself. So it's very modular in design. Then we've moved on to building digital twins of the BMS, from the philosophy of airline industry, physical machine versus digital twin. It was very popular so as to predict the remaining useful life of a aircraft and health management of aircraft. Same story. We started to look at digital twins of battery packs, so that now uh, this simulation and control, we can start working with the battery digital twin. We can use the historical data storage. You can actually use the measured and reported data, and finally predict the states of health and state of charge and the parameters estimation that we need to do, remaining useful life, etc., etc. So obviously, there's measured and reported data that goes within the virtual space. This is the real physical space. The control parameters go back from the virtual space to the physical space. That is the basic idea of having a digital twin. And this is only in this case, of course, some of you have worked in various areas of digital twinning right now in different areas of your research. This is gaining a lot of popularity now with some of our industry partners. So yeah, so then there is a role for the IoT in a digital twin based BMS. Obviously, the battery pack sits at the physical layer. The middle layer consists of all the sensors, right? So ambient temperature sensor, cell temperature sensor, current sensor, voltage sensor, etc., which goes to an IoT platform. And finally, there is a remote device for analytics and data storage, right? So always, of course, the data goes between the physical space, virtual space, which is the digital twin, as I said, and finally the feedback goes back to the physical space. So obviously, the entire system together is an IoT platform, right? So it is used for this bidirectional data transfer and communication among each of the entities of the digital twin based battery management system. Therein lies a lot of the data driven techniques such as AI, ML, and cloud in the digital twin BMS, right? So as to use or to achieve real time data monitoring, state estimation, thermal management, um, other functions of the battery's cycle life, for example, feedback control of the real battery, and updating the virtual model from time to time based on a machine learning algorithm. It could be anything. It could be neural networks. It can be, I don't know, vector regressions, all kinds of ML techniques out there, which we have. There's another separate presentation I have which talks about ML based state of health prediction and state of charge prediction, which I'm not included in this talk today in the interest of time. But yeah, so obviously they have a vital role, right? And data is at a premium. That can be applied for second life applications also, for EV second life, battery second life, right? So once the EV is battery is used up to 30%, 30 to 40% of its original capacity, it becomes rendered useless for EV driving, like vehicles, but it can be used like 60 to 70% is remaining charge. So that can be used for stationary or other charging applications itself, like a stationary battery pack. So again, to remaining useful life estimation, safe useful life, state of available power, state of charge, state of health, we need the applications of IoT and digital twin, right? So as you can see here, first life, second life, end of life, right? So this plot clearly shows you the capacity fade that is happening in the first life. So here you've used about 70% starting from here. The remaining 70 to 20% probably you have used here. And then that remaining 20% till the end of life goes through. So then you can, of course, think of recycling in a clean fashion. So you used up most of the lithium even in the second life. Recent developments, as we have seen, a lot of risks. Um, Electric car fire risks, they look exaggerated, but they are real. Almost in China alone, data suggests 7 to 8 battery electric cars catch a fire per day. Um, Here you can see why it happens is because of the propagation of the fire happens within 5 minutes. Okay, typically, when you design a battery thermal management system or a fault tolerant system, you must be able to identify the fire and did extinguish it within that 5 minute window that you have. Otherwise, it will propagate quite fast, as you can see here, right? But why is this happening? Why are the fires even happening in the first place? Is again, we did some experimental tests and we've seen here are this data uh, was not published before. Okay, again, you can see, however, here the red one, which is the surface temperature of a cell. Okay, the core of the cell shows you the blue one. That's the real core temperature inside the cell. So that's differential about 10 to 12 degrees Celsius, which is a huge difference. What are you feeding back as a temperature to the BMS? Uh, it's not this, it is this red one, which is way lower. So the BMS understands that, oh, it's okay, but it's not okay. Unfortunately, the core says something else. So we really need to start estimating the core temperature a little bit accurately. So impact of temperature on battery health is quite simple to understand. Obviously, I square R losses, right? So internal resistance increases with aging, which increases heating. So surface temperature increases, battery life goes down, right? So it is a very vicious cycle, I should say. We started to use some of the advanced modeling techniques that we've started in our own lab to build this digital twin BMS for thermal management control. So this is some of the work that we have started now in our lab. As you see, we built some electrochemical model and coupled that with an electrothermal model in order to core temperature, estimate the core temperature. We run it under different drive cycles. So highway drive cycle, city drive cycle, two city drive cycles back to back, and one city drive cycle in the LA92. So we've seen the temperature. You can see the core temperature profiles over here in the red. All these are core temperature profiles. All right, versus the discharge current in the blue. So basically, once you discharge the currents through the model, you can see how the core temperature estimates come. And we are validating this using cells now that we have got with internal temperature measurement sensors, which are built into the cell. Now, these are very niche, only to our lab. These are not commercially available. Um, in the past, researchers used to probe the cells. Imagine the cell probing it into the core to get that temperature thermistor, so the temperature would be dead. But now the problem is they were uh, changing the physical attributes of the cell, which defeats the purpose. In real life, you're not going to do that. So really, when your model wants to accurately predict within a certain range, we will need an embedded. There's no other way. Like we've tried X-rays and so like different other things which we thought would work, but not it's not accurate enough to give us the core temperature. So we had to go with a company that is based out of Canada, incidentally, um, in the Maritimes, in the Halifax area. If you guys are familiar with the Canadian geography, which is even further than Eastern time zone by 1 hour. Anyway, so that company we met at APEC recently in Orlando, Florida, APEC, IEEE APEC, and they said because if you attended APEC, you know that the exhibit is the best in the world, right? Their exhibition, so Expo. So we met them. They said, yeah, we can build you these cells. So they kept their promise. They've sent the cells to us with these embedded sensors in it, so we don't change the physical properties. So anyway, so we've started some validation work as well for this. Then we're looking at hybrid models with deep learning, core temperature estimation, cloud-based battery monitoring and estimation. As you can see, we've started that work now, where the BMS is in the AWS cloud. You can see here. Here you can see a proposed architecture of our cloud-based state estimator. Some algorithms like feed forward neural network, FNN, LSTM, which is long short-term memory, gated recurrent unit GRUs. We started to run them and we've started to compare them. prediction errors, looking at prediction error, mean average error, as well as the RMS error. And then this cloud server is actually physically located in a region of Montreal in Canada. So we've started some real work here with the AWS. So yeah, as a conclusion, for this part of the lecture, digital twin-based BMS and thermal management control system, we've started to develop. One of the primary requirements is the online state estimation in the cloud. We've started some work on a working prototype for an online SOC estimation of a single cell. So we've developed in AWS, which is located in Montreal, and it's validated in the lab environment. You saw there's a hybrid ECM based 2D grid long short-term memory, or 2D GLSTM neural network based cell core temperature estimation technique that is being developed. The thermal model is still on the second order, whereas we have a separate paper where we've developed a high order thermal model as well. And wide range of battery test data can be used for this experimental validation, which we've done in the lab. And finally, you saw a proposed concept of a digital twin based battery thermal management control system, right? And we have a patent pending for that as well. So with that, I'll end my talk. I believe we are on time. Thank you very much for listening, and I can open the floor up for questions.
Hello, sir. Sir, I had a question regarding the CTCV profile that you are proposing. There I saw that the cell temperature for charging is, as per the data sheet, is around 0 to 50 degrees centigrade. And the CTCV experiment that you have conducted at 2C, the maximum peak temperature there is around, not exceeding 30 degrees centigrade. So I
Yeah.
wanted to check with you, like, is there a like up to what temperature can we go when we are considering the CTCV profile?
Good question. So the question is, of course, about the maximum temperature permitted
Right.
by the cell. That again depends on the chemistry, right? It depends on. Recently, we started working on. This was about NMC cells, which you saw. There you have the maximum of about 45 to 50 degrees Celsius. Whereas if you look at LTO cell, lithium titanate oxide, more recent, high power cells, more capacity, but lesser in energy, you will find that their temperatures can go up to 60 or even 70 degrees Celsius. All the way from negative 30, you can also see the negative part of it, negative 30 to plus 60 degrees Celsius. So a wide range. So again, it depends on the manufacturer. But in terms of the study that was conducted, it is more around the gradient, right? The temperature gradient, not so much about the maximum temperature. We have not driven it to its maximum temperature or close to the stipulated temperature like 50 degrees Celsius. So I hope that answers your question.
Sir, good morning, sir.
Good morning.
Sir, my question is that when we are going for wireless BMS, we will have simultaneously cyber security issues, right? So how we are taking care of that?
Not yet. I will be very honest. We are not experts in software. Yeah, we are working with some software experts on that as part of our team. It's not my expertise, and that is a separate presentation which could be answered by some experts in software engineering or networking, communication networks, etc. But our work is centered still around the electrical part, which is the modeling and looking at temperature, is looking at the current profiles, etc., etc. We've not yet addressed the cyber security issues, which is going to be the biggest hurdle in terms of data safety and security.
Yeah.
No doubt, no doubt. It's work in progress. We just only recently, like I said, not even a year, right? This work has been ongoing.
Hello. Since I think that you're in Canada, so good afternoon. And okay, I'm actually a MTech student from Amrita. And
it's
my question is,
here.
I was
It
actually
is almost
working on
good
the
night.
same as a paste paper as what you mentioned, 2DG LSTM. And I happen to just notice that you are one of the authors. So I have some questions regarding the overall architecture of the LSTM itself, but I'll maybe mail you separately, since that's not
Yeah, it can be a
right time
long
to ask.
discussion. Just
My question
discussing
is,
the paper Yeah, sure. Send me an email, and yeah, it can be a longer discussion because again, that would be better if you read the paper, send the email. I'll connect you to the right folks who have worked on it within our group as well. Yeah.
So my base question is, in your paper, it is mentioned that RMSE you achieved was around 0.3 to 0.9%, which is approximately 0.2 degrees different to 0.81 degrees. That's mentioned in the paper, and you also mentioned in the presentation that it's not good enough, and we need to actually improve the performance of the prediction models. So, what is the expected, as per the industry standard, what we need to achieve? And do we
Well,
have sufficient data available in the public domain to actually work on it?
no,
Thank
so
you.
that's the problem, right? Yeah, very good question. Data is actually not available. We need to do more cyclic tests and more temperature-based cyclic tests as well to achieve that data, and the accuracy amounts would be really closer to 0.1 or within the 0.1% range.